A new study points to why and how Io became the most volcanic body in the solar system. Scientists with NASA's Juno mission to Jupiter have discovered that the volcanoes on Jupiter's moon Io are each likely powered by their own chamber of roiling hot magma, rather than an ocean of magma. The finding solves a 44-year-old mystery about the subsurface origins of the moon's most demonstrative geologic features. A paper on the source of Io's volcanism was published on Thursday, December 12, in the journal Nature, and the findings, as well as other Io science results, were discussed during a media briefing in Washington at the American Geophysical Union's annual meeting, the country's largest gathering of Earth and space scientists. About the size of Earth's moon, Io is known as the most volcanically active body in our solar system. The moon is home to an estimated 400 volcanoes, which blast lava and plumes in seemingly continuous eruptions that contribute to the coating on its surface. Although the moon was discovered by Galileo Galilei on January 8, 1610, volcanic activity there wasn't discovered until 1979, when imaging scientist Linda Morabito of NASA's Jet Propulsion Laboratory in Southern California first identified a volcanic plume in an image from the agency's Voyager 1 spacecraft. Since Morabito's discovery, planetary scientists have wondered how the volcanoes were fed from the lava underneath the surface. Was there a shallow ocean of white-hot magma fueling the volcanoes, or was their source more localized? We knew data from Juno's two very close flybys could give us some insights on how this tortured moon actually worked. The Juno spacecraft made extremely close flybys of Io in December 2023 and February 2024, getting within about 930 miles, 1,500 kilometers, of its pizza-face surface. During the close approaches, Juno communicated with NASA's Deep Space Network, acquiring high-precision, dual-frequency Doppler data, which was used to measure Io's gravity by tracking how it affected the spacecraft's acceleration. What the mission learned about the moon's gravity from those flybys led to the new paper by revealing more details about the effects of a phenomenon called tidal flexing. Io is extremely close to Mammoth Jupiter, and its elliptical orbit whips it around the gas giant once every 42.5 hours. As the distance varies, so does Jupiter's gravitational pull, which leads to the moon being relentlessly squeezed. The result? An extreme case of tidal flexing, friction from tidal forces that generates internal heat. This constant flexing creates immense energy, which literally melts portions of Io's interior. If Io has a global magma ocean, we knew the signature of its tidal deformation would be much larger than a more rigid, mostly solid interior. Thus, depending on the results from Juno's probing of Io's gravity field, we would be able to tell if a global magma ocean was hiding beneath its surface. The Juno team compared Doppler data from their two flybys with observations from the agency's previous missions to the Jovian system and from ground telescopes. They found tidal deformation consistent with Io not having a shallow global magma ocean. Juno's discovery that tidal forces do not always create global magma oceans does more than prompt us to rethink what we know about Io's interior. It has implications for our understanding of other moons, such as Enceladus and Europa, and even exoplanets and super-Earths. Our new findings provide an opportunity to rethink what we know about planetary formation and evolution. There's more science on the horizon. The spacecraft made its 66th science flyby over Jupiter's mysterious cloud tops on November 24. At the time of Periyov, when Juno's orbit is closest to the planet's center, the spacecraft will be about 3,500 kilometers above Jupiter's cloud tops and will have logged 1.039 billion kilometers since entering the gas giants.